Yaskawa Electric America's Technical Training Services would like to welcome you to the Braking Methods e-learning module. My name is Paul Anderson, and I will be your instructor today as we go through this e-learning module. This e-learning module will provide a basic overview of the available braking methods in Yaskawa AC Drive and show you how to determine which method to use on your application. During the course, we will cover three main topics: an overview and description of each braking method, a side-by-side comparison of each braking method, and finally, examples of braking method selection to show you how to determine the best method for your application. Four types of braking methods are available in the 7th generation Yaskawa Drives: DC injection, high-slip braking, dynamic braking, and line regeneration. The simplest form of braking is DC injection. DC injection works by sending DC current into two phases of the motor. This DC current causes a static magnetic field to occur, which attempts to lock the rotor in a fixed position. During the braking process, all of the kinetic energy from the load is transferred into rotor losses, most notably heat in the rotor. As you can see, one of the greatest benefits of DC injection is that the function is built into the drive. No additional components are required, preventing any additional cost when using this braking method. However, DC injection has low braking torque compared to the other braking methods, which yields longer stopping times. Notice also that the duty cycle is dependent upon the specifications of NEMA MG1 Part 20. Motor sizing and parameter configuration determine the actual duty cycle for the DC injection function. High-slip braking is a braking method that uses an algorithm to maximize the motor losses during braking. Output frequency is stepped down at various intervals to increase the negative slip in the motor. This large negative slip causes the motor to act as an inefficient generator so that during regeneration, all of the regenerated power is dissipated in the motor itself due to its own inefficiency. High-slip braking is an excellent selection for large inertial loads. No extra equipment is needed, and it can provide stopping times that are approximately 50% faster than without high-slip braking. Case studies have even shown that stopping times can be faster than 50%, which is a result of the fact that there is an increased amount of braking torque. The major drawback to high-slip braking is the increased motor heating resulting from the majority of the energy being transferred in to motor heat. Dynamic braking allows the motor to regenerate power back to the drive. As the DC bus voltage rises, a transistor turns on, allowing additional DC bus power to be dissipated onto a resistor grid. Dynamic braking is an excellent method of braking because of the available braking times and because it also applies to when the drive is merely decelerating and not just performing a complete stop. Also, duty cycles and braking torques can be determined by the user. The major drawback is the added cost. On the smaller units, only resistors are required. However, on larger units, both the resistors and braking transistor units are required. This additional cost can be up to 25% of the drive price. A special type of braking called line regeneration is also available. As the motor regenerates during braking, the regenerated power is sent back to the drive's input power lines through an active converter using IGBTs. In order to use line regeneration, an additional line regeneration module and input reactor are both required to be installed on the application. Except for the drawback of the additional cost, the line regeneration is by far the most superior method of braking. Because the regenerated power is transferred back to the electricity and not heat, the duty cycle is continuous. Also, because the regenerated power is sent back to the power source, the regenerated power can be recovered and actually reduce the lifetime cost of the unit. Line regeneration modules come in two forms. The first module is the RC5. The RC5 is connected to both the input power lines and the DC bus of the drive. During normal operation, input power is routed around the RC5 and through the drive's normal converter section. However, as regeneration occurs, the additional power on the DC bus is routed through the RC5 and back onto the power lines. Because the RC5 is not a complete replacement of the drive's converter section, it is a smaller package than what is seen on the next module, the DC5. The DC5 is a complete replacement of the drive's standard converter section. Both input power and regenerated power are routed through the converter section in the DC5. The DC5 module is larger than the RC5, but it is also capable of handling much larger drive sizes. Looking first at braking torque, both line regeneration and dynamic braking offer much more torque than high slip braking or DC injection. This is important when determining the braking method to be used because the stronger the braking torque, the faster the stopping time. Next is the duty cycle. Because line regeneration converts regenerated power back onto the AC input lines, there is no heating of braking components to be concerned with. This is why the duty cycle for line regeneration is so much larger than the other methods. Dynamic braking offers standard packages between 3% and 10% duty cycles. Custom dynamic braking packages are available which increase the duty cycle of dynamic braking, but as the duty cycle increases over 50%, it is often recommended to use line regeneration instead. High slip braking and DC injection duty cycles vary depending on the parameter settings and the motor sizing. The duty cycle is subject to meeting the NEMA MG1 Part 20 standards. Last, let's look at the additional cost incurred by the various braking methods. Although high slip braking and DC injection may not offer the same braking torque or duty cycle as line regeneration or dynamic braking, the advantage of these two methods is that they are built into the drive and require no additional cost being added. Dynamic braking can cost up to 25% of the drive's price, whereas line regeneration can cost even up to 50% of the drive's price. Comparing the application to these criteria enables the correct braking method to be determined. Different drives have different braking method availabilities. This chart shows which braking methods are available in each drive. For high-end applications requiring line regeneration, only the F7 and G7 are equipped to handle the RC5 and DC5 regeneration modules, whereas dynamic braking is capable with the P7, F7, G7, and V7. DC injection is a built-in function available in all 7th generation drives. Once the braking method is determined, this chart, along with the control requirements of the application, will guide you in selecting the appropriate drive for the application. Consider a mixing application where a fully loaded mixer must be brought to a stop. The duty cycle is around 5%, but the braking torque requirement is almost 50%. Comparing the application to the duty cycles provided for each braking method, all braking methods meet the duty cycle requirements. However, DC injection is not capable of meeting the braking torque requirements. This leaves line regeneration, dynamic braking, and high slip braking as the available methods. Because the application is a high inertial load, the high slip braking method would be the best method because it meets the requirements and it requires no additional cost. Next, an application that has a repetitive deceleration but not stopping of a medium load. The duty cycle is around 10%, but the brake torque is only about 25%. Because DC injection and high slip braking are only used for complete stops, they are not viable options. Both dynamic braking and line regeneration meet the duty cycle requirements, and all braking methods meet the braking torque requirements. Dynamic braking is most suitable for this application because it meets all necessary criteria, but it is less expensive than line regeneration. Last, consider a crane application that has approximately a 50% regenerative duty cycle. The braking torque requirement is near 90% when lowering an object near the rating of the crane. Both dynamic braking and line regeneration meet the duty cycle and braking torque requirements for this application. However, because a custom dynamic braking solution is required for this large duty cycle, line regeneration would probably be more effective. Here is a flowchart that can be used as an aid when determining the appropriate type of braking method to use. This is a general recommendation, and actual braking solutions depend on issues such as size constraints, complexity of the solution, acceptable heating, power quality, and cost. The appropriate braking solution is shown in yellow. Note that there are two dynamic braking solutions shown in the bottom right-hand corner of the slide. If the drive is less than or equal to 25 horsepower, only dynamic braking resistors are required, which help to lower the cost. If the drive is over 25 horsepower, both resistors and transistor units are required. Let's review what we've covered about braking methods. Yaskawa offers 4 types of braking methods in the 7th generation drives: DC injection, high slip braking, dynamic braking, and line regeneration. Using the data regarding duty cycle and braking torque of these methods, select the braking method that best meets the requirements for your application. Thank you for attending this Yaskawa Electric America e-learning module. We greatly appreciate you taking the time to learn more about our products. If you would like additional training, please contact us through any of the methods above. Thanks again and have a great day.